Hi guys, in the last lecture we covered the concept of symmetrical components. There we saw to analyze an unbalanced system it is very difficult as each KVL equation involves more than one current. So we cannot separate out the current in terms of different equations. We have to solve all the equations simultaneously to arrive at the result. So we saw a theorem called as Fortescue theorem, which enables us to break the unbalanced system into a set of balanced phasors and one set of cophasal quantities. So in that way I can analyze the balanced system much more easier because I have to analyze only a single phase and rest of the phases can be calculated directly by 120-degree phase shift. Okay. So in there we saw that it can be broken into three sequences: positive sequence, negative sequence, and zero sequence. Zero sequence means cophasal quantities, that is they are having the same phase. So we saw that we saw the phase shift operator which enabled us to write different phases of a same sequence in terms of a single variable. So we saw that 1 plus alpha square would be 0, alpha cube would be 1, alpha square conjugate would be alpha. Then we saw that convert between the phases and the sequences we can use a matrix one alpha square alpha 1 alpha alpha square V0 V1 V2. And to derive the sequence components or symmetrical components from the phase voltages, we can use the inverse of this matrix, which is 1 by 3, and we replaced alpha by alpha square, VA, VB, VC. Okay. And we saw that line component 0 sequence is equal to IN by 3 and line voltage 0 sequence component is always 0. That we covered in the last lecture. So in this lecture we will focus our attention to how to design the circuits or equivalent circuit for different sequences, that is for positive sequence, negative sequence and zero sequence. How to design different circuits each for a different sequence. So let us first start with a star connected winding. In this star connected winding we have the neutral grounded by a impedance Zn. In A phase current is IA, IB and IC. Now why I am considering a star connected winding is because a winding concept can be taken directly to a alternator where there will be winding, and as well as a transformer there will be windings. So hence first of all we are considering a star connected winding. Here current IA will have three components: IA0, IA1 and IA2. Similarly, IB will have three components: IB0, IB1 and IB2. Here I am assuming that the currents are unbalanced: IC0, IC1 and IC2. So this way there will be three components in all the currents. Now if we calculate IN, that is the neutral current, will be equal to IA plus IB plus IC, and as we derived in the last lecture, this is equal to 3 times IA0. That is only zero sequence current will flow through the neutral. Now let us consider one by one each sequence, that is positive, negative and zero sequence, to understand how you can draw the equivalent circuit. First of all, positive sequence network. For positive sequence I have only shown the positive sequence current flowing in the windings, that is IA1, IB1 and IC1. So I have neglected the negative and the zero sequence component. Now by KCL, neutral current IA1 plus IB1 plus IC1 must be 0 because the balance sum will be 0. That means neutral voltage, which is minus IN into Zn. Why minus? because neutral current will be flowing like this, so it will be plus minus. So this will be 0. Now if we wish to calculate the voltage here, VA1 will be equal to minus IA1 into Z1, because plus minus will be like this. Okay. So how can I represent this in the circuit form? This is represented as a reference bus that is having a 0 potential. Then this is a positive sequence impedance Z1. Current is IA1. Now this will be VA1. Here it will be plus minus. So VA1 will be minus IA1 into Z1. Now what is this Z1? What is the positive sequence impedance? This we will see when we will start considering the alternators and the transformers. Then you will easily understand what is meant by the positive, negative and zero sequence impedances. Because up till now what we have seen is just the positive sequence voltages and currents. Never we have talked about the impedance. And I only told you that Fortes theorem can only be applied to voltages and current and not the impedances. Then how come this impedance is arising, which is a positive sequence impedance? Physical significance we will see with regards to the different components of the power system. Next is the negative sequence network. Similarly, in negative sequence I have considered only the negative sequence currents, that is IA2, IB2 and IC2. Now in this case the neutral current will be IA2 plus IB2 plus IC2, which will be 0. Okay, that means the neutral voltage again, which is equal to minus IN into Zn, will be 0. If we apply KVL, VA2 will be equal to minus IA2 into Z2, because plus minus will be here. Here Z2 is the negative sequence impedance. To represent this as a circuit, this is reference bus, this is Z2, this is IA2. So it is VA2. VA2 is minus IA2 into Z2 plus minus. Okay. So that is how we can draw the negative sequence network. Now let us proceed to the most interesting part, that is the zero sequence network. Here I have only shown the zero sequence current IA0, IB0 and IC0. Now here the neutral current, which will be equal to IA0 plus IB0 plus IC0, which will be equal to 3 times IA0. That means the neutral voltage, which is minus IN into Zn, will be minus 3 IA0 into Zn. Hence, if we apply KVL, Vn minus IA0 into Z0. Earlier Vn was 0, so I was directly writing minus IA1 into Z1 or minus IA2 into Z2. Minus 3 IA0 Zn minus IA0 Z0. Now if we combine these two terms, I can write minus IA0 Z0 plus 3Zn. So neutral impedance appears as 3 times the neutral impedance in the zero sequence network. So how will my circuit look like? This will be the reference bus. This will be 3Zn, Z0, that is VA0, IA0. Okay. So that is how we can draw the zero sequence network from a star connected winding. Now here we were considering Zn. So there is a chance that Zn may not be connected to the ground, it may be isolated. So if Zn is isolated, that is, it will not be connected to ground, so Zn can be taken as infinity. So the zero sequence network will be affected. It will be shown as open circuit. Okay, because there is no current. Now this means no zero sequence current can flow. And anyways it is true, if we do not connect the neutral, no zero sequence current can exist. And this is pretty much visible from the zero sequence network. Okay. Now suppose if Zn is, or the neutral is, solidly grounded. Solid grounding means that Zn is 0. Zn will be taken as 0. So the circuit will be Z0, then it will be shorted. So VA0 will be minus IA0 into Z0. Zn will be taken as 0. So these are the two extreme cases in which neutral is not connected to ground or the neutral is directly connected to ground. That is why I was taking Zn initially, because then we can derive these two cases directly. So this was all about your star connected network. Now let us consider the delta connected winding. If the winding is delta connected, then this is the zero sequence current IAB0, IBC0, ICA0. Now I know zero sequence components are all equal. Okay. So these are all equal. So it is flowing like this. Now if I want to calculate IA0, that is the zero sequence component in line current, by KCL I can write it as ICA0 minus IAB0, which will be 0. So there is no zero sequence current in the line, but zero sequence current can easily exist in the phase. So how to represent this fact that zero sequence current can exist in the phase but not in the line? What we will do is, we will take reference bus. This will be Z0 and it will be connected to the reference bus. And this line will be shown open here. That is, zero sequence current cannot enter the line, but it can keep on circulating in the phase. Though this circuit might not look practically correct to you, but it is just a representation to indicate that zero sequence current can exist in the phase but not in the line. Okay. So that is how we draw the delta connected zero sequence network. And positive and negative sequence network will remain same because they are not dependent on the neutral grounding. So these are general concepts for the star and the delta connected winding, how we draw the zero sequence circuits or the positive, negative and zero sequence network. Now let us proceed to the first component of the power system, which is a alternator. So first case we are taking for the star connected alternator. Now here we have shown three EMF, EA, EB and EC, and the neutral is grounded by impedance Zn. Now in case of a star connected alternator, let me first show you the schematic of alternator. This will be A phase, this will be B phase, this will be C phase. Now we know whenever the prime mover or whenever the rotor lies along any phase, maximum EMF will be induced in that phase. Now if rotor is lying along this, then maximum EMF will be induced in A. Then when the rotor moves by 120 degree, then maximum EMF will be induced in B. And then when it again moves by 120 degree, maximum EMF will be induced in C. That means the order of maximum EMF will always be A, then B, then C. And they will automatically be displaced by 120 degrees. Why? Because they have the space displacement of 120 degree. Until you change the direction of rotation of the rotor, the sequence of maximum EMF will always be A, B and C, which is my positive sequence. So this statement I mentioned something like this, that only the EMF can have positive sequence, it cannot have negative sequence or the zero sequence. Why? Because until and unless you change the direction of rotor rotation, it will go from A, then B, then C. If it goes in the order of A, B, C, that means it is inducing positive sequence EMF. So keep this in mind. EMF can only have positive sequence, it cannot have negative or the zero sequence. That is, when we will be drawing the circuit, EMF will only appear in the positive sequence network and not the negative or the zero sequence network. Now let us first consider positive sequence. What is the meaning of positive sequence with regards to alternator? In alternator, we study that three-phase voltages or current induce rotating magnetic field. Okay, if they are inducing rotating magnetic fields, then what will happen is the rotating magnetic field will rotate at a speed ns. In case of positive sequence, it rotates in same direction as rotor. Okay, if it rotates in the same direction as the rotor, that means rotor is rotating at ns, magnetic field is also rotating at ns, and both are in the same direction. So relative speed becomes 0. Now one thing that you must clearly understand about the faults, suppose this is EMF, this is J-axis. Suppose a short circuit occurs here. Then the current IA1, if we find, or let us say IA will be EF angle delta by J-axis. So that is EF by axis angle delta minus 90. That it is 90 degree lagging, or we can say 0 power factor lagging. Now in a synchronous machine, if the current has a 0 power factor lagging, then what happens to the armature reaction? This is our field MMF. This is our induced EMF. Current is 90 degree lagging. So this is armature reaction, which is demagnetizing. Now in case of fault, since armature reaction will always be demagnetizing, there will be no problem of saturation. So under short circuit, the machine cannot saturate. But how do we represent the axis? This is D axis. This is my Q axis. So under short circuit condition, FAR or IA lies along D axis. Okay, it always lies along D axis. So the air gap or the reluctance that it will be offered will be corresponding to the D axis air gap. So the reactance that will be offered, armature reaction, will be XAD. Okay, so the reactance that it will encounter is leakage plus XAD, which is equal to XD. Now the one beautiful thing about this concept is, since it is a positive sequence, both are rotating at the same speed. That is, field MMF is rotating at a speed ns, and armature reaction also rotates at a speed ns. So it will always, they will always have a difference of 180 degree. So it will always lie along the D axis. Hence it will always be offered a reactance of XD. Thus positive sequence reactance is equal to direct axis reactance for the case of synchronous machine. Okay, but this further is divided into three categories, which I will explain later on how we define that three categories. First is XD double dash, which is subtransient reactance. XD dash, which is transient reactance. XD, which is steady state. Okay, so these are based on different times. Subtransient means in the initial 1 to 2 cycle after the fault. This is 3 to 5 cycle after the fault. It is greater than 5 cycles. Okay, so I hope now you understood the concept why we will be taking the positive sequence equal to direct axis, because in case of faulty condition, fault will have 0 power factor lagging. If fault has a 0 power factor lagging, then the armature current will lie along the d-axis. If armature current lies along the d-axis, then it will encounter the d-axis reactance or the synchronizing or the d-axis armature reaction. Okay. So hence positive sequence reactance is equal to xt. In case of negative sequence, what will happen? If current is negative sequence, then rotating magnetic field rotates at ns opposite to rotor. Now rotor has a speed ns. Rotating magnetic field also has ns, but they are in opposite directions. So relative speed will be equal to 2ns. Okay. So now if we see in terms of phasor diagram, this is my field MMF, this is EMF, this is IA, but now it is rotating at ns like this. This is rotating at ns like this. What we can do instead is, we can assume that this has the 0 speed and this rotates at 2ns with the relative speed. Now if it rotates at 2ns, right now it is lying along d-axis, but after 90-degree rotation it will lie along q-axis, then again along d, then again q, then again d. So it will alternatively lie along the d-axis and q-axis because it is rotating with respect to the field MMF or with respect to the rotor axis. So it will sometime lie along the rotor axis and at other time it will lie perpendicular to the rotor axis. So it will encounter the d-axis reactance as well as q-axis reactance alternatively. For half the time period it will have d-axis reactance, for half the time period it will have q-axis reactance. That means the reactance that it encounters is dependent on time. At some time it is xd, at other time it is xq. Then how to use some reactance? The best way out of it is take the average of the two. That is xd plus xq by 2. Now I know xq in case of salient pole generator is always less than xd because it has larger air gap as compared to xd. So that means x2 will be less than xd plus xd by 2, which is equal to xd. So x2 is less than x1. That is, negative sequence reactance is always less than positive sequence reactance. Okay. The difference in positive and negative sequences: in negative sequence the rotating magnetic field rotates opposite to the rotor, hence it encounters positive and negative sequence, it encounters d-axis and q-axis alternatively, whereas in positive sequence it rotates in the same direction, hence its relative position with respect to field MMF is fixed. Okay. So it always encounters d-axis. Okay. It never encounters q-axis. Is it fine? So that is why in case of negative sequence we will take average of d and q, whereas in positive sequence we will only take d-axis. In case of zero sequence, what happens? In case of zero sequence, since there is no phase shift, that means there is no rotating magnetic field. Now in case of alternator, how my windings are arranged? This is A dash, B dash, C dash. That means axis of A is upwards. Okay, perpendicular to this. Then axis of B will be at 120 degrees to this. That is FB. Axis of C will lie along this. Now, since all are having the same phase, FA will be equal to FM sin omega t. FB will be equal to FM sine omega t, Fc will be equal to Fm sine omega t. Since all are having the same phase, they will have same magnitude at each and every time. So their resultant will become 0. Three vectors oriented at 120 degrees with respect to each other having equal magnitude will yield a 0 resultant. It is similar to your phase shift operator. 1 alpha square, 1 plus alpha square is always 0. Similarly here, Fa0 plus Fb0 plus Fc0 will always be 0. Okay. So, since the sum is 0, it does not create any rotating magnetic field. It only encounters the leakage reactance. Okay, there is no armature reaction. Net flux is 0. So, armature reaction will not be present because armature reaction is created due to the net flux produced by the rotating magnetic field. But here there is no rotating magnetic field. The net flux is 0. So, there is no armature reaction. Only reactance is XL. So, X naught will be equal to XL. Okay. So, here we saw that X1 is greater than X2. It will again be greater than X0. Because X1 and X2 also had the armature reaction component, but X0 only has the leakage reactance. So, this is the physical significance of the positive, negative and zero sequence reactances of the alternator. Positive sequence is equal to direct axis because fault power factor is 0 lagging. Armature current always lies along the d-axis and there is no relative motion, so it will encounter d-axis reactance. In case of negative sequence, the MMF rotates at 2 times ns with respect to field, so it encounters d-axis and q-axis alternatively, and hence we take the average of the two. In case of zero sequence, no rotating magnetic field is formed and net flux is 0, so no armature reaction, only leakage component is considered. Now what happens for the case of delta connected alternator? Now in case of delta connected alternator, the problem will be we can draw the circuit, but there is no reference bus as there is no neutral. So we have to convert it to star. Here we will take the EMF EA by root 3, EA by root 3, EA by root 3, because if line voltage is EA, phase will be EA by root 3. And while converting from delta to star, the impedances will become Z1 by 3. Now in case of star, positive sequence would be reference bus EA Z1. This is IA1. So this is VA1, which will be equal to EA1 minus IA1 into Z1. But what to do in case of delta? In case of delta, what we will do is we will divide it by root 3, divide this by 3. So VA1 will be EA1 by root 3 minus IA1 Z1 by 3. This is your star connection. Sorry, this is your delta connection, positive sequence network. What happens for the case of negative sequence? In case of star, since there is no EMF in the negative sequence or the zero sequence, we will just place the impedance. This will be IA2. So VA2. VA2 will be equal to minus IA2 into Z2. But in case of delta, what you will do is you will divide it by 3. So it will be IA2 Z2 by 3. Similarly, in case of zero sequence, in case of star, what will happen? There will be no EMF, just the zero sequence impedance Z0, plus we will have 3 times the neutral impedance as we derived for the star connected winding, like this. So VA0 will be minus IA0 Z0 plus 3Zn. Okay. But in case of delta connection, there is no neutral grounding, so this will be taken as open circuited. That means IA0 will be equal to 0. Zero sequence current cannot flow in the lines of the delta connection. So that is how you will draw the equivalent circuits or the sequence networks for the case of positive, negative and zero sequence in case of star and delta connected alternators. Okay. So here let me summarize. Star, delta. In case of star, how does my positive sequence network looks like? EA, Z1, IA1, VA1. In case of delta, how does it look like? EA by root 3, then Z1 by 3, IA1, VA1. In case of negative, we will remove the EMF because EMF is always positive sequence Z2, IA2, VA2. Here we will have Z2 by 3, IA2, VA2. Okay. And in case of zero sequence, we will have Z0, 3Zn, IA0, VA0. Here we will have Z0, but it will be open circuit, no neutral impedance. Sorry, this will be Z0. So IA0 will be 0. So these are the sequence networks for the case of alternators, both star and delta connected. So let us summarize what we covered in this lecture. We first saw the star connected winding, the sequence network for star connected winding. Here one important thing that you must remember, in zero sequence neutral impedance appears as 3Zn. Then we saw delta connected winding. Here we saw zero sequence current can exist in phase but not in the lines of the delta connection. Then we saw star connected alternator, and the first thing that we observed was EMF can only have positive sequence, it cannot have negative or the zero sequence. Why? Because it depends on the direction of rotor rotation. If rotation is fixed, then negative and zero sequence cannot be induced. Okay, so EMF is always positive sequence. Then we saw positive sequence impedance was equal to XD because armature current was always lying along the D axis as the fault power factor was 0 lagging. Then we saw negative was equal to XD plus XQ by 2 because field was rotating at a speed of 2ns with respect to field MMF, hence it will encounter D axis and Q axis alternatively. In case of zero sequence, no rotating magnetic field was present, so it was equal to XL. In delta connection, what we saw is we have to take EMF as EA by root 3 and reactance as Z1 by 3 because we will convert delta to star before drawing the circuit. In the next lecture, we will continue drawing the sequence networks for the other components in the power system, that is your transformers and the transmission line, to know how to draw the sequence networks for the entire power system. That we will cover in next lecture.